Hello, my name is Mihai-Valentin DUMITRU from the University Politehnica of Bucharest, and today I will talk about my joint work with my colleagues Dragoș DUMITRESCU and Costin RAICIU. We make a first step towards answering the question of whether we can exploit buggy P4 programs. We know from classical programming languages that bugs oftentimes have negative security implications. In particular, we're interested in those bugs which trigger undefined behaviors, which are behaviors prescribed by the standard to have unpredictable and unreliable effects. What actually happens depends on a variety of factors, such as the compiler and the platform on which the program is run. For example, consider the following C function. It takes a zero-terminated string from an user and copies it into a fixed-size local buffer. What happens if the provided string is longer than the size of the buffer? The answer is that this behavior is undefined. On an x86 platform specifically, the buffer will be allocated on the function stack frame right below the saved return value, which is the address of the instruction executed after this function ends. Thus, a malicious attacker could craft an input that fills up the space to the saved return value, then overwrites it with an address of their own choosing, gaining control over the execution flow of the program. A bug which triggers an undefined behavior leads to an exploit that provides arbitrary code execution. These sorts of attacks and their connection to bugs have been thoroughly studied and understood in the world of C. We want to gain similar insights about the world of P4. What kinds of undefined behaviors are described by the standard? What are their concrete effects on real P4 targets? And could we exploit P4 programs in ways similarly to how we can exploit buggy C programs? Our work consists of two parts. First, we write simple buggy programs which trigger undefined behaviors in order to document the actual effects on three P4 targets. The simple switch target of the P4 behavioral model, which is a software simulator designed for early testing, the P4 net FPGA, and the barefoot Tofino. We also describe a few exploits on P4 programs. Let's begin with some examples of undefined behaviors and their actual effects. First, we look at reads from invalid headers. In P4, headers are similar to structures, but they also contain an implicit validity bit. All possible headers which the program can deal with are always syntactically in scope. For each packet, the parser marks as valid and populates those headers present in the packet. All other headers are invalid, and the standard specifies that reading from them yields an undefined value. We code a simple program which deals with two kinds of packets, distinguished by Ethernet type. Good packets contain an Ethernet and an IPv4 header, while faulty packets lack an IP header. Whenever we encounter a faulty packet, we read an arbitrary value from the invalid header and overwrite part of the Ethernet header. We then send the packet back and inspect it to see which value was read. On the simple switch, we get a value from the previous good packet. This suggests that headers are not cleared out between packets, which could lead to data leakage. However, on both the netFPGA and Tofino, we get a value of 0. Let's look at another behavior that is not fully specified by the standard, namely whether it is possible to create infinite loops. There are no looping constructs in P4, such as a while or a for loop. However, packets can be sent back for reprocessing through various methods. A resubmit will send the packet from the ingress deparser back to the ingress parser, while egress-to-egress cloning sends the packet from the egress deparser back to the egress parser. We want to see what are the effects of employing these primitives to implement infinite loops. So we run a simple program which deals with two types of packets. One of them is simply forwarded, the other endlessly recirculated. The results are as follows. On the simple switch, continuously resubmitting a packet results in the ingress pipeline getting blocked. Any further incoming packets are dropped. Continuous egress-to-egress cloning results in an endless stream of packets which floods the output port. On Tofino, for safety and efficiency reasons, we can only resubmit a packet once. Thus, there is no infinite loops that blocks the ingress pipeline. However, egress-to-egress cloning has the same effect as on a simple switch. A single input packet results in an endless stream of packets. As for the P4 net FPGA, unfortunately, at the time of writing, it did not support either of the reprocessing mechanisms. Another behavior not fully specified by the standard is the mechanism for dropping a packet, which is architecture dependent. There is no return statement or exit function. The standard suggests dropping should be achieved by modifying specific metadata, either by setting a drop boolean or by setting the output port to a special drop value. Because packet processing continues after being marked for dropping, the second method makes it easy to accidentally revive a packet further down the line. Consider the following example. First, an access control list is applied, which decides to drop the packet setting its output port to the special drop value. But then execution continues to the LPM table, which might decide to forward the packet, setting the output port to a valid value. Even though the packet failed the access control, it has been revived. These are the dropping methods of some common architectures, and those we used on the simple switch and the NetFPGA respectively, dropping involves setting the output port to a special value. On the portable switch architecture, there is a drop boolean. Now we've gone through a few examples of undefined behaviors, together with their concrete manifestations on actual targets, and we've got some hints of the problems that these may lead to. So we move our attention to some examples of exploits on P4 programs. We demonstrate our exploits on an example from the P4 programming tutorial, which implements network address translation. In our experimental setup, we have simple NAT running on a simple switch target and connected to a controller. We have an internal host and an external host. Here is the basic workflow for when the internal host wishes to send out a packet. Initially, there are no entries in the data plane tables, so a NAT miss occurs. Not knowing how to deal with the packet, the P4 program has to send it to the controller. It wraps it in a CPU header in order to preserve relevant metadata. Most importantly, the packet's original ingress port. The controller then inserts the appropriate entry into the NAT table and sends the packet back to the switch for reprocessing. Noticing the CPU header, the switch restores the packet metadata and figures out that it originally came from the internal host. This time, a NAT hit occurs and the packet is correctly forwarded. We now consider a powerful attacker who has full knowledge of the target as well as the program run on it and all of its table entries, and is directly connected to the switch. But our switch is configured in such a way that any packet coming from the attacker's port should be dropped. The attacker should not be able to send a packet to the external host. First off, we'll look at a very simple exploit. We've seen earlier that whenever it encounters a packet with a CPU header, the switch uses that header to restore metadata. However, the switch does not validate that a packet containing such a header arrived on the port connected to the controller. The attacker can fabricate their own CPU header, making it appear as if the packet originally came from the internal host. A NAT hit occurs and the packet is forwarded. For the next exploit, we delve into the inner workings of the simple NAT. First, the packet is passed through the interface info table, which looks at the packet's ingress port. Any packet from the attacker's interface results in the drop action being applied. Remember though that dropping on this target does not abort processing, but only sets the output port to a special value. So the packet reaches the NAT table, which looks at the metadata boolean to see if the packet came from an external port. Because the packet was dropped by the previous table, this value is uninitialized and defaults to 0, which is also the case for packets from the internal host. Then the table inspects the packet's IP and TCP source and destination. Having complete knowledge of table entries, the attacker can craft the packet with appropriate values to cause a NAT hit. Among other things, this action signals that the packet should be forwarded. Because the packet was marked for forwarding, the LPM and forward tables are applied, which perform the necessary rewrites for forwarding, including setting the output port to a valid value. Thus, the attacker's packet is forwarded as if it came from the internal host. So after looking at a few exploits and how they work, we should wonder about the bigger picture. What sorts of attacks are possible on P4 programs? What sorts of attacks are not? We first try to answer this latter question. We can easily disregard some classes of attacks. For example, because the code is immutable, there can be no code injection. There is also no instruction pointer, so no code reuse attacks are possible. In general, violating control flow integrity seems impossible. Use after free attacks are also not an issue because of the lack of dynamic memory management. However, there are some plausible attacks, such as data leakage, as you've seen when reading invalid headers on the simple switch, denial of service through endless recirculation, and spoofing, as in the simple NAT example. In summary, our paper takes a first step towards addressing the question of exploitability in the P4 world. We explored the actual manifestation of undefined behaviors on real targets and showed through several examples that exploits involving powerful attackers can be mounted against buggy P4 programs. In the future, we plan to explore weaker attackers and provide some more examples of exploits. We also aim to automate the process of bug discovery and exploit generation.